Welcome back. This video is very important in that I'm going to be introducing many of the concepts and the notation that we're going to be using for the rest of the class. So really watch this carefully. Then in the next video, I'm going to be illustrating a lot of these concepts with some simple forecasting models that we're probably going to want to use as I call them baseline models. When we compare against the more complicated models that we're going to be developing. Okay, so let's restate the basic problem. So the basic problem is I observe capital T values of my time series. So these could be my sales at time 1 through my sales at time capital T. I've said that they're roughly equally spaced in time. So it's really important that we have measurements at each time period. And when I say roughly equally, I'm allowing for things like months. So, January is a little bit longer than February. We're not going to worry about that. We may correct for it, as we did with the transformation that I mentioned a couple of videos ago. But what's important is that we get that measurement every month. We don't have any missing data. Okay, our goal in forecasting is to make a prediction of the future. And the notation I'm going to be using for that prediction of the future or forecast is going to be y hat at time period big T plus little h. So what this means is we're going to forecast 8 h periods ahead in the future, given what I know as of time t. So let me just go over to my document camera for a second. And the way I like to think about this is when time begins. And if you go 1 month in, we call this the first month or the first quarter. Then here is month 2. This is month 3. And this goes all the way through month T. So let's see. Month T would be this one. Now, this is officially the future, and I'm observing Y1, Y2, all the way through YT, and my goal is to make a forecast of what's going to happen here. So let's just put a little question mark there. My notation for what that value is going to be this. Since I don't know it, we're going to stick a hat on it, and that's my estimate of what's going to happen at time t plus 1. And often I'm just going to write it that way. But if I want to be extra precise, I will say given t. And so what that means is I'm allowed to use all the information that I have in y1 through yt to make a prediction of what's going to happen in this next period. So I'm not allowed to use information about the future. I can't use information about what happens at time t plus 2 to forecast t plus 1, but I'm allowed to use everything through time t. A few more terms. The seasonal period is the number of periods that we get in a cycle. So as an example, if I have monthly data, then presumably things repeat every 12 months, and the seasonal period would be 12. For quarterly data, the seasonal period would be 4. The next concept that I want to introduce is called a white noise process. And I'm going to be using the symbols epsilon 1 through epsilon whatever to indicate this white noise process. Now, white noise processes, think of them as just random. Everything about them is random. There's nothing to explain in a white noise process. So in particular, white noise processes are going to have mean zero. They're going to have constant variance, call it sigma squared, and no autocorrelations. So the correlation between any observation and another observation s periods away is equal to 0, so no autocorrelations. Now, from time to time, we're going to talk about a special type of white noise process, which is a Gaussian white noise process, where we add the assumption of normality. So white noise processes do not have to be Gaussian. They could be, uniform. They could be Bernoulli trials, whatever, as long as they have these properties that I've mentioned. Another concept that we're going to use a lot is stationarity. So a precise definition of stationarity is that the joint distribution of the next S values of my time series. So start anywhere you want and look at the joint distribution of S Y values. That doesn't change. So it doesn't matter where I start. When I look at the joint distribution of these S random variables, it doesn't change. And so what that really means is, the mean isn't going to shift, the variance is not going to change, and the correlations between these will not change. So we can think of stationarity as kind of a much weaker concept than a white noise process, but it's not changing over time, and so that's a kind of a desirable property in a lot of situations. The last concept that I want to introduce at this point is a prediction interval. So whenever we make a forecast, we'd like to be able to put a little bound on it that quantifies where I think the real value in the future is going to lie. And so that interval that specifies a range where I think the future observation will lie is a prediction interval. So I think the simplest way to understand this is let's say that our y values are normal, and so let's call this y t plus 1. So this is what's going to happen next. And if we know that it's normal and we know the standard deviation of this distribution, what we know from basic properties of the normal distribution is that about 68% of the time we'll be within one standard deviation of the mean. Okay, so this interval would be called a 68% prediction interval because it's giving me a window where 68% of the time what happens next period will fall in there. We also know that if we go roughly 2 standard deviations out, we get 95% of the area under that curve. And so 95% of the time, what happens next month occurs between here and here. So this is the lower PI, lower end of the PI. This is going to be the upper end of the 95%. Let me be a little bit more precise, PI. So PIs always have a probability attached to them, and it's just a window where we think this future value is going to fall. Now, what we're going to find is that some forecasting methods will enable us to get more precise prediction intervals than other methods, and we're going to prefer those that give tighter prediction intervals. So this is going to be just kind of a standard thing that we're going to be producing whenever we make a forecast. So just a few more terms and language that we use. So I introduced this notion of y hat t plus h given h. We call this an h step ahead forecast at time t. And as I mentioned earlier, when I use this notation, I'm not allowed to use any future values in computing the forecast. Otherwise, it's not a forecast. So when we build a forecasting model, we usually divide our data into a training set and a test set. So what I'm going to be assuming is that we're going to use observations 1 through big T to train our model. And then often we're going to have some future values, so call them T plus 1, T plus 2, and so forth, that we're going to use to evaluate how well our forecasting model has done. So this is very much like what we did in machine learning, where we had a test set which wasn't used in training the model, and that was kind of an independent measure of how well the model did. Now, we've got some special names associated with both the training and the test set. So the fitted values refer to predictions on the training set. So y hat t, say given t minus 1, where this t is less than or equal to big T, is a fitted value. While if I go past big T, we call that a forecast. So these y hat values in the test set are forecasts. They're fitted values in the training set. Likewise, if we look at the error, so the error is just y sub t minus y hat sub t given whatever information we're using. On the training set, we're going to call that a residual. On the test set, we're going to call it a forecast error. So we're going to use exactly the same symbol, but just to be clear, we'll use slightly different names for them. Now, there are a couple assumptions that we're going to be making with our models. The first two are, I'm going to say, strong assumptions. So we want our errors to be uncorrelated, and the reason for that is if our errors are, still have some correlation structure in them, what that means is, we're kind of leaving, leaving something on the table where we could do additional, we could build a better model by, taking care of that correlation structure. So if we could model that explicitly, we'd actually get better forecasts. So for that reason, we'd like for these to be uncorrelated. A second strong assumption that we have is that these residuals should have mean 0. If they don't, then your forecasts are biased, and you've got some work to do on your model. Now, there are two other assumptions that, let's say we sometimes need these, sometimes we don't. And so the first one is that we have constant variance. The second one is that the errors are normal. So if we're going to be computing prediction intervals, we need a normal distribution. We kind of need the constant variance for that. But if all we're doing is making a forecast, these are not really necessary with most of the methods that we're going to be studying. Okay, so I've called them nice to have, whereas these are really important. The next question that I want to address is, how do I know how well my forecasting model is doing? The way we're going to answer that question is really similar to the way we answered it for regression. So if you remember what we did in regression, we looked at the sum of squared errors or the residual sums of squares, depending on which textbook you're looking at. So it was a summary of the residuals. And we're going to do exactly the same thing with our forecasting models. The book gives about 6 or 7 of them. I'm just going to present 4 that I'm going to say are probably the most common ones. There's a couple of others in the book that are also used, but this will give us a flavor of what's going on. The first one we've seen in machine learning, the mean squared error. And so what the mean squared error is, just take your errors, your residuals, and square them and compute the mean. And so the way to think about this is, what is the average amount that your forecast is off in squared terms? That's literally what this is saying is, the error is how far you're off. We square it to get rid of the sign, and then we're just looking for a description of the typical size of the amount that we're off in squared terms. So that's the mean squared error. A problem with the mean squared error is that the units are squared units, and we usually, we prefer to have our summaries in the original units, and so the way we can take care of this is just taking the square root of it. And so if we measure something in centimeters, Mean squared error would be in squared centimeters. Root mean squared error would be in centimeters, just raw centimeters. Mean squared error is centimeters squared. So that's going to be one of the most common measures that we use. An alternative approach to this, the reason we square these errors in the mean squared error and root mean squared error is to get rid of the sign. Because some of our errors, sometimes we overestimate things, sometimes we underestimate things, and by squaring it, we get rid of that sign. A different way of getting rid of the sign is to take the absolute value. So just, convert all the negative errors to positive errors, and then average them. And so both the root mean squared error and this mean absolute error are trying to tell us what is the typical size of an error, and they just estimate it in a different way. The last measure that I want to discuss is called MAPE. So MAPE is the mean absolute percentage error. And so the whole idea here is we're going to take the error and divide it by the observed value, y sub t. So in other words, we're downweighting very large, the errors for very large y's. We're weighting up the errors for smaller y's. And another really useful property of this is that it's unitless. So if the y's are measured in centimeters and the errors are measured in centimeters and they cross out, so that's a very desirable property, that it's a unitless quantity, kind of like r squared. Then what we do is we just take the average of this, and we tend to multiply it by 100 to get percentages. Okay, one caution with this, you need ratio data. So what I mean by ratio data is you need to have a meaningful zero. So zero has to mean the absence of anything, as opposed to something that doesn't have a meaningful zero, like temperature measured in degrees Fahrenheit or Celsius, because what you'll find is that you can shift the origin then and manipulate this thing to be whatever you want. So zero has to be a meaningful quantity, meaning the absence of whatever you're measuring. All right, so we can compute these four measures either on the test set or the training set, and then I tend to prepend either training or test in front of it. So I'd say the test set mean squared error or the training set mean squared error, depending on whether I'm using the fitted values and residuals or the forecast and the forecast error. So I want to talk about one more approach to evaluating time series models. So this is called time series cross-validation, and it's very similar to k-fold cross-validation that we used with machine learning models. So here's the basic idea. Instead of having some fixed test set and training set, so I'm just going to use the first capital T cases for my training set, and then I've got a few other cases for my test set, I want to have a rolling one. And so here's what I mean by a rolling one. So we're going to begin with some initial set of cases that I use to build, call it an initial model. So sometimes with the simplest estimators, that model might only take one observation to train. Others times it might take, say, 10 observations, and I would set that with this initial option. Okay, so now I have an initial model with the first few observations. Then what I do is I forecast the next observation. So if I have an initial data set of 10 cases, I use the first 10 cases to estimate the 11th case. Then what I do is I update my model, and I use the model that's been estimated on the first 11 cases to predict the 12th case. I update the model, so I use the first 12 cases to estimate the 13th case, and so forth. And I do that until I get to the end of the data. Then what I do is I compute my accuracy metrics using only the values that are one-step look-ahead forecasts. So we don't use the initial observations in computing that. So the advantage of this is that you will have larger test sets usually, because you're not having to set aside a big chunk of your data for your training set. And so this is going to be the method that we tend to use most often. But both the training test split and this one both work. Okay, in my next video, I'm going to illustrate all of these concepts on 3 simple models.